example number 5, and specifically there we go. All right, we're in unit number 5, example number 5 on page 10. And our example here starts us out with a demonstration with a hockey puck. And I can actually do this one on the video, so I'm going to go ahead and kind of set this up a little bit. I've got a hockey puck. It's actually not a real hockey puck, but it's a little hockey puck that's got a hole at the bottom. You can kind of see that there. And then it's got kind of like a stopper here, and there's a hole in that stopper, and you can barely see it maybe right there. And what I'm going to do is I'm going to blow up this balloon, put it on here, and it's going to push air through this hockey puck, and then the air is going to come out the bottom. And if I put this on here, this hockey puck is going to float on a cushion of air, and it's going to be not perfectly friction-free, but somewhat friction-free. And it'll be able to move on its own, and that'll help us answer some of the questions that we have coming up in example number 5. So let me blow this up. And then, ever so carefully, try to put this on here, and I'll try to hold this so you can see it. So I've got it there. I've got my finger over the hole in the bottom so it doesn't leak air, and then here it is. And then it'll float nearly friction-free. You can't really see it real well with the video, but you get an idea. And so if it's at rest, my question for you would be, if it's at rest and now it's moving, the question is, how does it get moving? So like here, it's at rest essentially right now, and then how does it get moving? And you know, I pushed it, and by pushing it, I made it move. And it will continue to do this until it runs out of air, and then the friction will overwhelm it and bring it to rest. And there it is. Okay, and it doesn't slide as well as what it just did. All right, let me zoom the camera in. We're going to use that concept to answer these questions. All right, so the first question is, how much kinetic energy did the puck have at the beginning? And the beginning was when it was at rest. So it was kind of confusing probably with that demonstration. So we're going to say that the beginning it has 0 joules. So we'll put 0 joules into there. What form of energy did the puck have, or what form of energy did the puck acquire? Well, if I pushed it and it started moving, it would acquire kinetic energy. And the evidence for that is the fact that it was in motion. All right, next one. From where did the puck get its new energy? So it didn't have kinetic energy, and all of a sudden it had kinetic energy. Where did it get that energy from? Well, it came from me. It came from the fact that I pushed it. And by pushing it, I did work on it. And remember, work is a transfer of energy. So by doing work on it, I gave that puck energy. So my energy level went down, and the energy level of the puck went up. What work was work done on the puck? The answer is yes. And then how do you know this? Well, we know it because it changed speeds. If it changes speeds, you know that work was done on it. Its kinetic energy changed because it had 0 at the beginning, and then it had some amount of energy at the end. When was work done on the puck? This is a good question. Work was done on the puck only while I was pushing it, because while I was pushing it, it sped up. But after I stopped pushing on it, so after I tapped it, it went at a smooth speed. It didn't speed up anymore. So when was work done on the puck? Only when I pushed the puck. Only while my finger was in contact with it. All right, now we got those down. So now let's go to questions L through N on page 2. I'm sorry, on page 5 of example 2 of your notes. So we're going to go way backwards. And page 5. Let's see if we can figure this out. This was a long time ago. So we're on L, and we want to calculate how much kinetic energy the box acquired. So we're going to have to kind of figure out, how much did it have, and then calculate how much energy it picked up. So Let's just go ahead and go back to the beginning of that question. In the beginning of that question, I think we're going to have to scroll all the way back to, it looks like, page 3. So if you go back to page 3, here's the question. Let's just reread it so we kind of have a feel for what's going on. It says, draw a free body diagram of someone dragging a 60-kilogram box 10 meters with a force of 200 newtons at an angle of 60 degrees with the floor when friction is 40 newtons, and then label all forces. So it looks like this object was at rest at the beginning, and then it sped up because someone pulled it. And I think if we look back, let's go back to a previous page here. Yeah, right here. If we go to page 5 of your notes, letter H said, if the object started from rest, how fast is it traveling after the first 10 meters of pulling? So it did start from rest, so it's kind of like a hockey puck. It started from rest and it picked up speed. And right here, 4.47, that's how much energy, that's how much speed it had at the end of that period of time. And so we're going to need that. So the question down below, this is letter L now, same page, says calculate how much kinetic energy the box acquired. Well, kinetic energy is 1/2 mv squared, 1/2 times the mass of the box. All right, now we got to go back and find the mass of the box. And I have a feeling that's a couple pages ago. Yep, there it is right there. The mass of the box is on page 3. Mass of the box is 60 kilograms right there. So I'm going to use that. That's letter L now. So 60 kilograms. And then the speed of the box, that's what we had up in letter H. So that's 4.47 meters per second. And then you want to square it. All right, now let's go ahead and plug all of that in. So this is 0.5 times 60 times 4.47 times 4.47. All right, and we get, basically, I'll round that off to 600. Let's just say 600. So 600 joules. So once it got up to that speed of 4.47 meters per second, it had basically 600 joules of kinetic energy. All right, letter M. How does the kinetic, this is an important one, how does the kinetic energy the box acquired compare to the work done on the box from parts E and G? Okay, so let's go back to parts E and G. Now E is at the top here. Look at what E said. It says the net work done on the box was 600. That's interesting. We calculated 600 down below here for the kinetic energy, and the work done was 600 joules. Do you notice that those are the same? So the work that you've done is equal to the kinetic energy of the object. What about letter E? Yeah, there it is, letter E. 600 joules as well, and that's the net work done as well. So can we, now let's answer letter M first, I guess. So how does the kinetic energy the box acquired, how's the kinetic energy the box acquired compared to the work done on the box from parts E and G? They're the same. The kinetic energy that the box acquired is equal to the amount of work being done. And if that's true, then let's see if we can put an idea together. Look at letter M. Based on your answers from L and M, what conclusion can you make about the net work and the kinetic energy? Well, we can say the net work that's done is equal to a change in kinetic energy. And that's an important one. As a matter of fact, that right there, now go back to page, that's a long time ago. Go back to page 5. Look at what happened to the puck. The puck was at rest. It's the same thing. The puck was at rest and it gained a bunch of energy. So any work that you did on the puck, given to the puck through kinetic energy. It's the amount of kinetic energy that the puck acquired. Well, let's use that over here. So we're going to derive the kinetic energy equation from the work energy theorem. So the work energy theorem is what we just kind of came up with just a moment ago. And the kinetic energy theorem says the work that you do is equal to the change in kinetic energy of that particular object. All right, so if we know that, then we can do a little bit of a derivation. And actually, we're going to start someplace different here. I kind of misled you. That's what we're going to finish up with. All right, we're going to derive the kinetic energy equation and the work energy theorem. But we're going to derive it. So when we derive it, that means that's going to be the last thing that we get, not the first thing. I started with that, and that's actually what we're going to end with. We're going to start with something that we already know, and that's Newton's second law. And we know that Newton's second law is F equals ma. But I also know that I have an equation for acceleration, and the equation for acceleration is going to come from an old big 3. And I'm going to take this equation and solve for a. If I solve for a, I get vf squared minus vo squared all over 2d. Then I'm going to take that, substitute into this equation, and then work a little bit of algebra. So I'm gonna move the d to this side, so I get this. And then I'm going to multiply the m over 2 into this parenthesis. So I've got, let's see if I can squeeze it all on the frame. It doesn't look like it's going to let me do that. So I've got sum of all the forces times d is equal to, now I'm going to do m times vf squared all over 2. There's the first part. And then I'm going to take this m over 2 and multiply it times the VO. So it's minus mVO squared over 2. Now, look at what we've got here. This is mv squared over 2. Isn't that just the same thing as kinetic energy, 1/2 mv squared? Isn't that the same thing? So I can kind of play with that a little bit. And I can get 1/2 mv squared and then minus 1/2, this is the final here, mvo squared. Alright, now, one more step. Look at this. What's force times distance? Isn't that the net work right there? So isn't this the work that's done? Net work. Sigma F is net, by the way. So it's the net work that's done is equal to, this is final kinetic energy, minus initial kinetic energy, which is also equal to a change in kinetic energy. Look what we just did. We've done two different things. First of all, we derived what we talked about earlier, the fact that any work that you do to the object is going to cause the kinetic energy of that object to increase. So we've got that one. But also look at what we've got here. We came up with this term. This term, that right there is kinetic energy. We've given that a name. So we have just derived the kinetic energy equation, which is right here, and the work kinetic energy equation, which is right there. So we've done two things. So the next question is this. What is kinetic energy? Is it a scalar or is it a vector? Well, look at work. We know work is a vector, is a scalar. So that means if kinetic energy is equal to work, then and work's a scalar, then kinetic energy must be a scalar as well. All right, how come? Because there's no direction associated with kinetic energy. All right, on the next video, we'll start out with example number 6.